Hi, people. Let's talk about lasers. I'll try and keep this reasonably short, but also give you the information that you need. So, lasers. Let's really quickly start off with what laser light is. Laser stands for light amplification by stimulated emission of radiation, and the key here is amplification. Amplif amplification. Light is the important thing, and by stimulated emission is key. So, what does all that mean? Well, here is the deal with it. Amplification of light is about producing, if we think about the nature of laser light is very high intensity because it has a very large amplitude due to the fact that all of the photons are in phase with each other. So if we wish to make a laser, we need to produce light. We need to produce photons that are in phase. That is absolutely critical. How do we go about doing that? Well, to understand that, we need to know a little bit about energy levels and about electrons. You guys will all already be aware that within an atom, within a molecule, within a substance, electrons have certain allowed energy levels for all sorts of reasons that I'm not going to go into today. Um, the electrons can exist at their lowest possible energy, which is generally referred to as the ground state. Ground. Um, and this is an energy diagram, by the way. This isn't the sort of position of electrons. This isn't their whereabouts. This is just a diagram of energy. So let me just label that energy. Increasing energy is this way. So the ground state is the lowest possible energy state for electrons. And that's where they'd like to be. In general, nature tends to move things towards their lowest energy state. So if I was to look at a substance, I would find that all of the electrons are in their lowest possible energy state most of the time. However, they can move up to higher energy levels. You guys will be aware that there are lots of available energy levels within a normal material, but I'm only interested in these two for the time being. So let's call this upper one the upper energy level. How do they move into those positions? To get up to that higher energy state, they need to absorb energy. So that can happen if a photon is absorbed by this electron, it can promote it. But there are rules to this. The energy of the photon, and remember photon energy is given by Planck's constant times frequency, the energy of the photon must match the energy difference between these two levels. So this HF that I've drawn here must be equal to the energy difference between ground and upper. It must be. Otherwise, this electron can't absorb it. It's as simple as that. The electrons can't exist in an energy state that's somewhere halfway between or somewhere beyond this one. They've only got the options to hop between energy levels. They can't be somewhere in between. So this process would be called absorption. This is absorption because the electron has absorbed a photon. That has promoted the electron to this higher energy state. In general, an electron in a high energy state will decay or will fall back down to the lower energy state. And we call that spontaneous emission because when it does that, it will emit a photon. So here is, let me draw it over here for you. Here is an electron in that elevated energy state. It will fall back down. And as it does so, it's going to emit a photon. Here is that photon. And again, the energy of that photon, which is HF, must be equal to the difference in energy between those two states. Absolutely must. This is emission. Does emission have two M's? I'm not sure. In a normal material, most of the time, this process would happen spontaneously. So I'm going to put in brackets above that, spontaneous. And what that means is it happens unprompted, and for pretty much all materials, it happens virtually instantly. So an electron that's been promoted like this will spend an incredibly short amount of time in this elevated energy state before it falls back down. So we started with a photon of energy of energy HF. We've ended up with a photon of energy HF. These two photons have the same amount of energy. I haven't gained anything by doing this. This is not a laser. This is essentially useless because what's happening here is spontaneous emission. What we want to happen is stimulated emission. So here's the thing. In some materials, and those materials in some cases are natural, in some cases are engineered by clever people. In some materials, there can be an upper energy state that is metastable. So I've still got my ground state, I've still got my upper state, but this upper state is metastable. And let me explain what that means. What that means is that if an electron is promoted to that metastable state, it does not instantly decay back down. It stays there for some time. So I'm going to put in brackets after that long-lived, if you like, long life, whatever. It's a long-lived state. By long-lived, we're talking long-lived in the time scale of tiny particles. So we're still talking about a minuscule fraction of a second. I'm not going to invent numbers, but it would be a tiny fraction of a second. But nevertheless, compared to what normally happens, that is a long time. What that means is if I shine in a whole bunch of photons, here come some photons. Again, these photons have to have that correct energy. They have to be of the difference in energy between the two states. These photons can be absorbed. They can promote electrons upwards in the process of absorption. But these electrons will not necessarily fall straight back down. They will stay in this elevated state for a short amount of time. What is interesting about that is that if one of these photons of this much energy passes an elevated electron, if one of these photons interacts with one of those elevated electrons, it does something interesting. It causes that electron to fall back down, but it doesn't get absorbed in that process. The electron falls back down and emits a photon necessarily of the same energy. And so now I've got two. Also importantly, the second photon that is emitted is in phase with the first, traveling in the same direction. We can use the word identical. It's an identical photon. So what that means is if I have an electron in this upper state and an incoming photon passes it, it will fall back down, emitting an identical photon. And so I've then got two photons. That is okay. This process is called stimulated emission. Stimulated rather than spontaneous because it's been caused by that passing photon. Stimulated emission. Now, why is this helpful to us? Well, if we have a bunch of photons coming in, these photons can be arbitrarily absorbed by these ones in the lower state, in the ground state, causing them to be promoted. These incoming photons may or may not be in phase. However, these photons are perfectly in phase. And that's brilliant. If these two pass another one in the upper state, it will also it'll also decay by stimulated emission, and I could then have three photons all in phase. So while it doesn't appear that I'm getting anything out, because for each one in this upper state, to get there, it must have absorbed a photon of the same energy. So I'm not gaining energy here, but what I am doing is I'm taking photons that were not in phase and making them in phase. So this is now lasing, if you like. There are problems. There are significant problems. The big problem here that we've got is my photons that have been created, here they are. Um, yes, they can cause a further stimulated emission, and that photon will then be in phase with these first two, but they probably won't, because these photons can, of course, be absorbed. Rather than causing a stimulated emission, they can be absorbed and they can cause an electron to be promoted. That is a problem. The probability, if I suggest that there are Ng electrons in this lower state and there are Nu electrons in this upper state, the ratio of probabilities, the probability of stimulated emission divided by the probability of absorption is equal to the ratio of those numbers. So if I have my pair of photons here that have been, one of which has been produced by stimulated emission, and I want that to become 3 photons and then 4 and then 5 and then 6, all perfectly in phase with each other, what I need is for it to be more likely that stimulated emission occurs than absorption. And for that to happen, I need more electrons in the upper state than in the lower state. That should be a capital G. This is called population inversion. Having more electrons in the upper energy state than the lower energy state. And if you think about that just for a moment, nature doesn't want that. Things do not in general want to exist at higher energy states. Nature always rolls downhill. So that is virtually impossible to create in this two-level system that I've got here, because by default, all the electrons initially live in the ground state. So the ground state is always essentially full of electrons, if you like. It always has a large number of electrons in it. So we've got a bit of an issue there, that these photons that are being produced could well be absorbed rather than causing stimulated emission. How can we get around that? Well, the obvious answer seems to be to throw in lots of photons here. This process of chucking in huge numbers of photons that are going to be absorbed to promote electrons upwards is called pumping. So we pump electrons from the ground state to that upper state in an attempt to achieve population inversion. That, however, causes another problem. Let me explain. The problem that's going to be caused by that, let's suppose I'm doing a vigorous amount of pumping. Let's suppose I'm pumping at a good rate, and therefore I have large numbers of electrons in this upper level, because I'm putting in large numbers of pumping photons. The problem I've got, I want to convert the photons I'm putting in, which are not in phase, to ones which are in phase. That's what my laser wants. That's what I want my laser to do for me, to get amplification of the light. I need the light coming out to be in phase. The problem is, if I'm flooding this area with these photons, then there's a very high chance that one of these photons triggers stimulated emission, and that isn't in phase with these ones. So that's a problem, and I need to think of a way to get around that problem. Luckily, there is a way. So the way we get around that problem, so I'm going to have to do very fast pumping in order to try and achieve something even close to a population inversion. The way we get around that problem is we don't just have 2 levels, we have 3. And here is, let me label them up again. Here is my ground state. Here is my upper state, but here is the level that I'm going to pump to. Ground state, as always, has a large number of electrons in it. This time, my incoming photons need to be of energy E, which of course equals HF always. That needs to be equal to the difference in energy between the ground state and the pump level. When those photons are absorbed, they're going to promote electrons all the way to up here. This is a normal energy level. It is short-lived. So these electrons will essentially instantly decay and pop back down to this level. This upper level, this is my metastable level. So they'll stay there for a little time. Sooner or later, one of them will spontaneously decay. As it does so, it's going to emit a photon of size E equal to the difference in energy between G and U. That photon can then cause stimulated emission. Here is a stimulated emission, causing that one to drop, and I then get 2 photons, and then 3 and 4 and 5, etc. All perfectly in phase. These are in phase. They have been created by stimulated emission. But I have skillfully avoided the problem of, if I need to create that population inversion, I need to pump very quickly indeed to constantly be feeding this upper level with electrons and constantly removing electrons from this lower level. So I want as few electrons in the ground state as I can get and as many in the upper state as I can possibly get. Let's remind ourselves, so that the probability of this photon causing a stimulated emission is higher than the probability of it being absorbed. So I have to have a lot of pumping photons, loads of them. But these pump photons are not of the right amount of energy to cause a stimulated emission. So by having this 3-level system, this is a 3-level system, I can avoid that problem, and I can get a laser that actually works. I can produce a laser where I can throw in lots of light. This is pumping happening over here. And yes, I've lost some energy. This transition here will be emitting energy. I don't care about that. That is a spontaneous decay. Maybe it's emitting it as photons. Maybe those photons are lost. They're not in phase. I don't care about that. This is these photons. Each one of these has cost me a pump photon for sure, but these are in phase. That's the important thing. So I have managed to turn a large number of photons not in phase into the same number of photons, albeit photons with slightly smaller energy, that are in phase. And that's what my laser is. Now this system is still not great. It's still not perfect. And the reason it's not perfect is, look, I've still got a lot of electrons in the ground state, in the lower state. So my photons that are being produced by stimulated emission can still be absorbed. They can still cause promotion instead of causing stimulated emission. So my system could be better still. So let's have a look at how we make it even better. So this is a 4-level system. And again, right at the bottom, I've got the ground state. The ground state always has a large number of electrons in it. Above that, I've got a lower state. Above that, I've got an upper state. And right at the top, I've got a pump state. So what happens here? I pump by shining in large numbers of photons of energy equal to the difference between the ground state and the pump level. Those are absorbed and elevate electrons to this top state. This is a short-lived state. So these electrons spontaneously fall to the upper level. The upper level is metastable, And remember, that just means they'll stay there for a non-zero amount of time. They won't instantly fall down from there. They will stay there for a little while. So if I'm doing enough pumping, then these electrons promoted to the pump state will constantly be feeding this upper level. But the key difference here is when I get one of these drop to the lower level, emitting my photon of energy equal to the difference between the lower and upper levels. These electrons drop to this lower state. This lower state is short-lived, so they do not stay there. That is the important thing. They instantly drop back to the ground state. The ground state can have as many electrons in it as it likes, so long as this state is short-lived. I will have achieved population inversion, a really good population inversion, not like previously where I had to continue pumping at a furious rate to try and maintain some sort of population inversion. This time, my population inversion is by virtue of the fact that this lower level is nearly always pretty much empty. So what that means is that this photon is very unlikely to be absorbed and very likely to cause stimulated emission, producing 2 photons, another stimulated emission, 3 photons, all in phase, and so on. So this process means that the number of photons in my material that are in phase is always increasing so long as I am feeding this upper level by pumping. And therefore, the number of in-phase photons continues to increase and increase and increase. So that's what's happening inside a laser. The material where this is happening is generally referred to as the gain medium, because that's where the gain happens, where we're gaining photons. And the way it would work, if I was to draw you like a diagram of how that would look, my gain medium might look like that. At either end of it, I place a mirror. One of those mirrors is only partly reflective. I say partly, 99.9% reflective. So this gain medium, for example, might be a solid, it might be a gas, there's all sorts of things it could be. It could be some sort of crystal. That's my gain medium. I shine in photons, and these are my pump photons, EP. I shine those in from all directions. They shine into this medium, exciting electrons. My stimulated emission electrons are then produced. Now, initially, some of those may be lost in random directions, but some of them will travel along this axis and they will reflect off the end. And once that starts to happen, those photons will bounce backward and forward inside here. So at any time, there will always be lots of in-phase photons traveling backward and forward. This metastable state holds electrons for longer than it takes for photons to travel twice the length of this gain medium. Remember, photons travel remarkably quickly. So if you're an electron up here, you really don't have to wait very long at all for a packet of perfectly in-phase photons to come past you, cause that stimulated emission, and you have dropped to the lower level and increased the total number of photons. So this number of photons bouncing backward and forward keeps increasing, but because this is not entirely reflective, each time a packet of photons bounces off this end, 1 in 1,000 escapes, and given that photons, the numbers that we would be dealing with would be enormous, 10 to the 20 or whatever photons bouncing off the end with each reflection. What that means is what comes out is a stream of photons that are all perfectly in phase. And that's it. That's how a laser works. How do I get rid of that? Yeah. So what type of questions do we have to be able to answer? First up, it's definitions. We have to be able to define population inversion. That's not how you spell it for a start. It's not pop-out. population inversion, and we have to say why it's necessary. So we've got to be able to define it and explain why we need it. And remember, population inversion means probability of stimulated emission is higher than probability of absorption. We have to be able to define stimulated emission. So remember, stimulated emission is about a passing photon of the correct energy. So of energy equal to the difference between the two energy levels, the upper and lower energy levels. A passing photon causes an excited electron to fall to a lower energy state. And importantly, that emits an identical photon. And that's where the gain comes from. One photon comes in, two photons come out of that process, and they are identical, i.e. in phase, traveling in the same direction. We have to be able to define pumping. And pumping is just the process of putting energy in to raise electrons from the ground state to the pump level. That can be done optically by shining in photons of the right energy, but it can also be done electrically using semiconductor lasers. I don't know what was happening in my brain there. That looks like deck trick. I don't know, it was freaking me out. I'm going to rewrite it. Electrical. So electrical pumping is where the gain medium is made from a semiconductor, and we use a potential difference in an electric current to excite those electrons up. So either way, we're giving the electrons energy. And that's it. That's my summary of lasers. The only other kind of what I haven't done is any sort of calculations. I'll leave that for you guys to investigate. The key thing to the calculations is to remember that it isn't the total. If you were given a diagram like this, you might be told that that's at 0 electron volts or 0 joules. Let's go with joules. That's at 0 joules. This might be at 1.38 times 10 to the minus 19. This might be at 2.09 times 10 to the minus 19, etc. The key thing to remember is that the energy of the photon must match the difference between the two energy states that it's moved between. And of course, the energy of that photon is equal to Planck's constant times the frequency. So therefore, if we combine that with the wave equation, C equals F lambda, we can say that the energy is equal to hc over lambda, and we can use that to calculate the wavelength of those photons. That's it. Hope it's helpful. GG.